Welcome back to Tracing the Sky. So in the last video, we started our series on Aristarchus. He is by far one of my favorite astronomers. He has this crazy goal. He's living back in like 300 BC, and he wants to see if he can figure out the distance from the Earth to the moon and the Earth to the sun. How far away are these things away from us? He also wants to figure out their sizes. And you just think about how crazy this is. With the technology they had at the time, nothing compared to what we have today. How is he going to figure these things out without ever leaving Earth? And this journey is just incredible. So let's start today by just recapping his main realization and look at how he was able to use that realization to start to make some progress. Because, before I learned about him, I wouldn't know where to start with this problem. How would you figure this out without leaving Earth? Well, let's remind ourselves what he did and see how he's able to use that to great effect. Okay, so let's start with Aristarchus's first big realization. And you might want to rewatch the last video if anything I'm going over today is a little fussy. We go over it in a lot more detail in the previous video. But his big realization is that when we see a half moon in the sky, right? So in the top right corner here, you can see what we would see from our perspective on Earth, right? Which is a half moon. So, half of the moon is still dark, half of the moon's illuminated that we see. That when we see that orientation, it must be that the sun, moon, and our position on Earth form a right angle triangle. That there's this right angle in this corner here where the moon is, and that we have a right angle triangle formed by these 3 points. That is hugely significant. We'll go over that in a second. Now, the first thing I just want to remind ourselves of is this green line here represents the distance from Earth to the sun, from our position on Earth to the sun. And this red line here represents the distance from our position on Earth to the moon. And that's what he wants to figure out, right? He wants to figure out exactly how many miles this is. How many miles away is the moon from our position on Earth? How many miles is the sun's position from us on Earth? So already he knows something now. He knows that these sides are part of a triangle, okay? And it's not just any triangle, it's a right angle triangle. And he knows a lot about right angle triangles. Remember, the Greeks knew a lot about geometry and triangles. So this is actually a huge piece of information. Now, why is it so significant? Well, let's just remind ourselves something about right angle triangles. If you draw a right angle triangle, okay, so we got this right angle triangle here. Now let me draw another right angle triangle. So if I draw another right angle triangle in green, you may remember from our previous lessons that if you have 2 right angle triangles that share the same angles, right? And you can see here that their left corner here is the same angle, right? This angle here, let's just draw it for you. This purple angle here is the same for both the red triangle and the green triangle. Well, that must mean that these 2 angles, these pink angles, are also the same. Now, check out some of the previous videos if you want a reminder of why that has to be the case. But we know that for right angle triangles, all of the angles add up to 180 degrees. So if they have one angle in common, then they also have this 90-degree angle in common. And so that last angle must make up the difference to 180 degrees. Again, the other video goes over that in a bit more detail, a little more slowly. Well, what we learned in that video is that the ratio of the sides of the triangle are the same between our green and red triangle. Obviously, the green triangle is bigger, right? It's taller and it's wider than the red triangle. So if you measure the sides, right, how long is the base of this triangle? How tall is the triangle? It's going to be different. But the key is if you divide them, right? So if you ask the question, how much taller is it that long? Or how much longer is the hypotenuse, right? This long line here compared to the height. That's when you find out the ratio of the sides is the same. That the amount it's taller or wider or the hypotenuse is longer than it is tall compared to the red triangle is the same. They have the same ratio of sides. And that is a huge realization. Now, why is that so significant? Well, let's have a look at our triangle over here between the sun, moon, and earth, right? We've said that this green line here is the distance from the Earth to the sun. That's one of the things that Aristarchus cares about. This red line is the distance from the Earth to the moon. Well, he knows that with right angle triangles, if he can find the angle, he can figure out the ratio of sides. What does that mean in our context? Well, he can figure out how much longer this green line is compared to this red line. Another way to say that is how much further away the sun is compared to the distance to the moon. So he can figure out whether the sun is further away or the moon is further away, and not just which one's further away, but how much further away, right? If he can figure out just one of these other angles, either this pink angle here, let's draw it, if he can figure out this pink angle here, or this other angle here, this more bluish angle here, if he can figure out one of these angles, he knows that the other angle is 90 degrees, he can figure out the ratio of the sides, right? If he gets one of those angles, he can draw a triangle on a piece of paper in the sand, right, in his hand, and he knows that the ratio of that triangle, the sides of that triangle, is the same as this right angle triangle here. And just think about how incredible that is. That's the power of geometry, right? This idea of a triangle and the sides and the ratio of the sides being the same applies to a triangle that's small enough to fit in your hand or large enough to span the distance between the sun, moon, and earth. That the idea of that triangle and its properties is the same no matter how small or how big that triangle is. And so even though you can't see this triangle directly, he has no ability to send a rocket up and take a picture of it and measure it. He knows that if he can figure out just one angle, he can draw a triangle with the same angles and then measure their sides and figure out the ratios. That is just remarkable and shows you the power of the human mind. Okay, so what is Aristarchus going to do? Well, he knows that if he can figure out one of these angles, right, this pink one or this green one, he can draw a triangle, measure the sides, and calculate the ratio. And that ratio, remember, is the relative distance of the moon and the sun. How much further away is the moon compared to the sun? Which one is further away, right? That's all we're really talking about, is comparing the lengths of these sides on our triangle. And those represent distances. We know that for any triangle, all of the angles have to add up to 180 degrees. We know this angle is 90 degrees. So if he can figure out the green angle or the pink angle, he can know the other one, right? And then he can draw this triangle, measure the sides, and solve this first step. So what's he going to do? Well, let's think about what these angles mean and how you might measure them. This green angle here, right, is the amount of turning from the Earth to the moon as seen from the sun, right? Remember, angles are measurements of turning that we do. So if you were standing on the sun, looking at the moon, and then turning to see the Earth, to look at the Earth, how much turning have you done? And that's this green angle. Well, he's probably not going to be able to figure out that angle first, right? He can't go to the sun and look back at the Earth and the moon. So can he figure out this pink one? Well, what kind of turning is this pink angle representing? Well, think about it. This is our position on Earth, we said. And he had this whole realization because he said, well, he can see a half moon in the sky. So we know he can look at the moon, see a half moon. And then the question is, can he also see the sun? Can he turn and measure that amount of turning from seeing the moon to seeing the sun? So can you see the sun in the sky when you have a half moon? Is that possible? I mean, this diagram would suggest that it is possible, that there are times when you can see a half moon and the sun at the same time. Well, let's have a look at the real sky and see whether or not we can make that sort of observation and measurement. Because if he can do that, if he can see a half moon in the sky and see where the sun is and take that measurement, take that angular measurement, he can tell us exactly what the angles of this triangle are, and he can draw his triangle. So let's have a look at what he does. Okay, so here we are, and we can see the moon in the sky, and you can see it's half a moon, and it's day out, so we can find the sun, right? And if we turn our heads here, we turn to the left, we can see the sun there. So we know now that Aristarchus would have been able to measure the amount of turning. In fact, I've actually put us in Samos, Greece. So this is way farther into the future than when he was making the observations. But you can see that from Greece, you can see a half moon in the sky at the same time that you can see the sun. And you can measure this angular turning. And that's exactly what Aristarchus did. Now, his measurement tools weren't as precise as us, so the number he got wasn't quite right. When Aristarchus measured this, he estimated it was around 87 degrees, that angle was 87 degrees. Think about that for a second. That's almost 90 degrees, right? 3 degrees away from a 90-degree angle. In reality, it's even closer than that. If you were to actually use our advanced measurement techniques and tools, you could use this, for example, to measure it. We can click this measurement tool in the bottom left corner, click on the sun and click on the moon. You would see that the angle is 89 degrees and a little bit more. It's actually very, very close to 90 degrees. It's about 89.85 degrees in reality. That's almost 90 degrees. So Aristarchus gets really close. He gets 87 degrees. And that tells him exactly what the angles of this triangle are, so he can draw the triangle and measure the ratios. Let's hop back over to our other diagram so we can really tie what we're seeing on screen here to what Aristarchus inferred about this. How do we translate this 87-degree measurement he got, or the 89-degree measurement we're getting, to our other triangle? Okay. Well, let's just label our diagram here and just orient ourselves a little bit, right? Aristarchus is standing on the earth in Greece, and he's looking out and seeing the half moon, and then he's turning and he's measuring the amount of turning from the moon to the sun. And that's this pink angle here. So he gets 87 degrees, right? Well, 87 is pretty close to 90, and you can probably already tell that this angle is way too small. Right? This is what a 90-degree angle looks like. This angle needs to be larger. Well, how do we make that angle larger? Well, we have to move this green line and increase it, right? This would be about 90 degrees. And so we have to go to 90 degrees and then a little bit less, right? 3 degrees less. So let's say it's around there. So you can see already this angle needs to increase. Well, you might notice a problem. These lines are no longer touching. This is not making a right angle triangle. Now, if this line was a 90-degree angle, these two would be parallel and they would never meet. But because this one is just less than 90 degrees, we know that eventually this green line and this blue line will meet if we make them far enough. So if we extend them far enough into the distance, so far they don't even touch on screen. My screen's not even big enough to show you, but if you keep extending these lines, they'll eventually touch because this line is less than 90 degrees. Well, that means you have to move the sun. The sun has to be way further away in order for this to work. And that's exactly what Aristarchus discovers, is that the sun is way further away from the earth than the moon. Now, how much further away? Well, I don't want to tell you that yet. In fact, I want you to draw a triangle with a 90-degree angle and an 87-degree angle. Draw that line, draw another line, and see where they touch. You might need a really big piece of paper to do this, but you'll be able to do this. Do it that way and then measure the length of your line, this green line here, and the length of the red line, and divide them. And that will tell you how much further away Aristarchus thought the sun was compared to the moon. And then what you can do is the same thing, except make this angle 89 degrees or 89.85 if you want to be really, really precise. And if you do that, you can figure out the actual answer. You'll be able to figure out exactly how much further away the sun is from the moon. So if you do those two things, you'll get a number. And in next week's video, I'll tell you what Aristarchus got and what the real answer is. Now, what's really remarkable about this is even though Aristarchus's measurement was off, even though he's 3 degrees off, his method is still 100% accurate. His method and his realization of this half moon and where the sun is and where the moon is conceptually totally valid. And if you get the right measurement, you're actually able to calculate the relative distance. So this is absolutely remarkable. So next time, if you join me, I'll give you the answer, and hopefully you'll have a chance to do it yourself, and we'll compare what Aristarchus does to the real answer, and I'll show you how this is significant and what he does next. because now he'll know how much further away the moon is compared to the sun. And that will be a huge piece of information along his journey to figure out how far and how big they are from Earth and compared to Earth. So I'll see you next time.